All right. Okay, it's over to you.
Okay. Well, thanks for the introduction. Hi, everyone, and thanks for the invitation to speak about my work in these very nice seminars, I would say. So in this seminar, I'd like to present our work, which is called Collective Monte Carlo Updates to Tensor Network Randomization. And this work is already posted in the archive under this ID a while ago, a bit more than a year ago. And I have also to mention that this work done in collaboration with Michael Marian and David Pérez García, and it's work done under the supervision of Mari-Carmen Manjuls, who's my supervisor here at the Max Planck Institute for Quantum Optics, and Sofia Nibrisir, who was my supervisor back in Barcelona. And yes, I've been very well said. Yeah, like feel free to stop me at any time to ask questions. I'll also appreciate that. And yeah, I was saying that this work is called Collective Monte Carlo Updates to Tensor Network Normalization. And the idea is to use tensor network techniques to power, which are a numerical method that was developed, say, in the early 2000s to study quantum many-body systems in one dimension. But since then, like, it has expanded and it's to many other fields. And yeah, like all across physics. And the idea was to try to use these techniques to, say, improve the existing performance of like Monte Carlo algorithms, which are very practical to study both classical and quantum many-body system. No? So just to motivate a bit this idea of sampling in physics or sampling in many-body physics, the paradigmatic example of a model that can be solved or like can be studied by using sample is the Ising model living in some lattice. No? And just to remind you, but I'm sure that you're all very familiar with it, the Ising model is like a model of binary variables, say spin up or spin down, that live on the vertices of some lattice. No? Well, the classical Ising model. And these particles interact with their nearest neighbor, and they have like an energy which dictates their equilibrium properties. No? And we know that if we study this model in the canonical ensemble, then the probability of having some configuration X is given, or it's proportional to the exponential of minus beta, which is the inverse temperature of the system, times the energy of that configuration. No? And then we know that under this probabilistic interpretation of the canonical ensemble, then the expectation value of some observables, for instance, the energy of or whatever observable, is just given by taking the expectation value according to this probability distribution. And as all of you, well, I'm sure that you know, the problem of these kind of models is that they live in an exponentially large configuration space. No? So the configuration space of individual spins is just made up of, like, say, spin up and spin down. But when I want to construct the configuration space of the entire many-body system, I have to take the tensor product of the individual spaces, and that gives me a configuration space which is exponentially large. No? And then any hope of trying to compute these sums, but yeah, like these expectation values directly is for like systems of a large number of particles is impossible, because then we have to do an exponentially large number of sums. No? And yeah, that's going to be impossible to do in practice. And something that one can also try to do is try to solve exactly these, say, analytically, these kind of models. No? But the models that are solvable analytically are very constrained. No? And in a generic case, say, if we want to study some particular model with some set of couplings and some set of degrees of freedom, it's going to be hard to find, it's going to be maybe impossible to find an analytical solution. No? So in this setting, what we need actually is to try to develop like some numerical method that allows us to, say, study the statistical mechanics of these kind of models. No? And something that one can do is to realize that if one is able to sample like independent samples distributed according to this probability distribution, these Boltzmann weights, and one is able to sample, say, a number of samples which is this n sub s, then one can evaluate on these samples any observable, and that's going to give you an estimate of the observable with a statistical error, so purely with a statistical error that decreases as 1 over the square root of the number of samples. And then the problem of like computing any observable, well, any expectation value of these many-body system is translated into the problem of just sampling this probability distribution. No? And well, but still, like, it's not easy to sample this probability distribution because it depends exponentially on the energy of the configurations, and this energy, well, like, this means that the configurations that are relevant for, say, a given temperature and a given instance of the model are exponentially localized on this configuration space. No, so we need to come up with a clever way to sample samples according to this probability distribution by fx. And the way that it's usually done in practice is through these methods which are called Markov chain Monte Carlo. And the idea of them is to construct a stochastic process, so say like a series of time-ordered events, ordered by like some parameter, to each all of them that we can assign some probability distribution. And the idea is to construct this stochastic process in such a way that at long times, the probability of having some given configuration approaches the probability of like this probability distribution of the Boltzmann weights. And in a constructive way to do so, and a particularly useful way to do so, because it's going to make easier to analyze these stochastic processes, is to enforce this Markov property, this Markovian property. And what this Markovian property basically states is that the probability of going to a new configuration given all the past of the say random variable, it's only going to depend on like the state of the chain, or well, the state of the process in the step immediately before. So say if the entire history of my stochastic process is this described by these variables, so from x1 to xn minus 1, in a Markovian process, the probability of transition into a new configuration xn it's only going to depend in the state immediately before. And a stochastic process that obeys this Markovian property is going to be called a Markov chain. And Markov chains are particularly easy to analyze because they can be theoretically studied just by doing linear algebra, actually. So the idea, because of this property, is that say the probability of having some the probability distribution of having some event at the time x can be computed from the at the time n can be computed from the probability distribution at the time n minus 1 just by multiplying by these transition probabilities. So this actually just can be understood as a matrix vector multiplication. And in order to construct this particular stochastic process that we're interested in, that has this Boltzmann weights as the limiting distribution, it is useful to choose a transition matrix that doesn't depend on the particular state. So take a homogeneous time-independent Markov chain. And this T is usually referred to as the transition matrix. And one can then see that, say, if I want to advance, say, k steps in the future with this transition matrix, the only thing that I have to do is to multiply k times by the transition matrix. So this is what I've written here in this equation. So if I have the initial probability distribution of being on some variable y, then by multiplying k times by the transition matrix, I can get the probability distribution at a later time k. And the idea is that if this T matrix were to have like an eigen decomposition, then the spectral properties of this transition matrix govern the Markov chain, because then if this has say like a largest eigenvector, and we start with a probability distribution that has some non-zero overlap with that eigenvector, then at large times we would see this eigenvector. So yeah, so basically what we have to try to do is to construct a transition matrix T that has sort of like as a limiting, has as an eigenvector the transition, the desired probability distribution. And the way to do so, the constructive way to do this is by using this property, which is called ergodicity. And the idea is that ergodicity is a combination of two properties. The first one is aperiodicity, which basically means that aperiodicity means that you don't move in your configuration space in a periodic fashion. So here I've thrown an example of a Markov chain that is actually not ergodic. So in this Markov chain, like it's not a Markov chain coming from, say, a many-body problem. It's just a Markov chain that transitions between these states that are labeled by capital letters. So this A, B, C, D, and the arrows between the different letters just point like whenever there's a non-zero transition probability to transition from one place to the other. So I was talking about this property of ergodicity, and ergodicity, I was saying that it's a combination of two properties, both aperiodicity and irreducibility. And the idea of aperiodicity is that you don't move across your configuration space in a periodic manner. So here I've drawn an example of a Markov chain that moves in a part of the subspace in a periodic manner. Because if you're in this state, say B, then you're going to be moving, like in a periodic manner. Like the only time that, so the only number of times that in which you're going to return to this initial state B is going to be a multiple of 4. So then I think it's quite obvious that you're moving in this configuration space in a periodic manner. So we want our chains to be ergodic, and then we want them to not be periodic. And the other probability, the other property that makes up ergodicity is irreducibility, which basically means that there's a non-zero transition and there's a non-zero probability of transitioning from any given configuration to any other. Here I've drawn as well something which is reducible, so the opposite of irreducibility, because it is impossible to transition from this configuration C to any other configuration in the system now. And the nice thing about ergodicity, about this combination of these two properties, is that we have it. If we have a Markov chain that is ergodic, then we know that there's going to exist a distribution, which I'm going to call pi as the Boltzmann distribution, because later we will take it to be the Boltzmann distribution, in such a way that it is, say, like an eigenvector of the transition matrix with eigenvalue 1, and it is actually the only eigenvector with eigenvalue 1. And also, like, the nice thing about it is that starting in any arbitrary initial configuration, at long times we're going to approach this probability distribution. And the way to do it, the way to that we approach this probability distribution is going to be exponentially fast, actually, in the number of steps that we take in this Markov chain. No? And that's going to be really useful, because if we're able to come up with, say, a transition matrix T that satisfies this equation with pi, the Boltzmann distribution, and at the same time this transition matrix T is ergodic for this scheme, then we will have a way to, just by running this Markov chain, we will have a way to sample from the desired probability distribution, the Boltzmann distribution. Okay, and a constructive way of finding this transition matrix T with an ergodic T is to impose this condition, which is called detail balance. So, it's usually called detail balance in the context of physics, and it's also referred to as reversibility in the context of applied mathematics. And basically, this condition states that the probability of being in a configuration X times the probability of transitioning from this configuration X to another Y is equal to the probability of being in a different configuration, well, on the other configuration Y, and transitioning back to this times the probability of transitioning back to this X. And this is actually true for any Y and any X. No? And one can actually see, it's quite simple, that if this condition is satisfied, then this global condition is also satisfied. And yeah, well, there's like another check that we still have to do, that we need to come up with that transition matrix T ergodic that satisfies this. You know? But I guess it should be clear right now that if this is satisfied, then this global condition is also satisfied. And the way to do so in practice, to find a T that is ergodic that satisfies this property, is by factorizing this transition matrix, no? Because this transition matrix needs to be some probability distribution on the entire configuration space that we have to be able to sample from in order to propose moves for this Markov chain when we are running it, no? And the way to factorize this transition matrix, to construct it explicitly, is to split it into two parts. So first, like, there's going to be a proposal probability. So so that's going to be the probability of proposing a move. So given that we are in Y, the probability of proposing the move to X times the probability of accepting this move that we've proposed from Y to X. No? And then the good thing about it is that as long as we choose a P general enough, in such a P that makes our transition matrix ergodic, then by taking this acceptance probability, which is called this Metropolis Hastings filter, then we're going to satisfy this detail balance condition. And okay, yeah, that's what I wanted to say so far. And something that I didn't stress already enough is that the different proposal probabilities are going to have an impact on the performance on our algorithm. No? So if I choose a proposal probability which is not that good, or like it's not that efficient, then my chain might have to like run for much longer to approach the desired the limiting distribution. But if I carefully pick up a useful proposal probability, then my chain might need like a small number of steps to reach the desired probability distribution. No? So what I'm trying to say here is that the proposal probability actually encodes sort of the performance of the algorithm. And in practice, in the context of statistical mechanics, simple proposals are chosen, no? Because it has to be to propose these moves. Like, so when we are running this chain, it needs to be something that we can sample from. So it has to be a simple probability distribution. And I'm sure that many of you know it, but like one of the most useful choices is to propose, take a proposal probability, which is either uniform or zero. And this is what is called like this spin flip algorithm. No? And to illustrate it here, I have, say, yeah, like a particular configuration of the Ising model, where I have like 3 spins up and 1 spin down. No? And this proposal, this proposal probability proposes a move to configurations that only differ by a single spin flip. No, so with uniform probability, if I'm in this initial condition, well, in this condition, in this configuration, sorry, I propose a move to any of these configurations that differ only by a single spin flip. But the transition probability from this configuration, or like the transition probability from this configuration to a configuration that differs by 2 spin flips is actually 0. No? And then this, I mean, like this should be clear that it's ergodic because it's clearly non-periodic, no? Like it's there's no periodicity on this scheme, and it's also like possible to move from like say any initial configuration to any other, no? Like you just have to pick the sort of like the appropriate spin flips to get there, no? And there's always a non-zero probability distribution from transitioning to one configuration to any other, no? In a number, like a given number of steps. And if we use the fact that this proposal probability is uniform, so it's the same for all the configurations that differ just by a single spin flip, then this acceptance probability on the Metropolis Hastings filter, like these factors that we had before of the proposal probabilities drop out, and then we just have like we just have to take the minimum of 1 or this ratio of probabilities, no? And by using the particular form of the Metropolis, the Boltzmann weights, I can actually see that the acceptance probability of a move is just related to the inverse temperature and the change in energy that I've made by flipping this spin. And yeah, I guess, well, like this is what is usually referred to as the spin flip algorithm, that I'm sure it's familiar to probably all of you. But this is like really the most basic algorithm that one can come up with to sort of like sample the Boltzmann distribution from spin systems, but it is not that useful, no? Because we know that as we approach, say, like criticality or like so systems like the systems that we study become more and more correlated, and then just simply by doing like individual spin flips is not such an efficient way to move across the configuration space, no? And then we need to sort of like be able to to move more efficiently across the configuration space. So what is actually seen in practice is that if one tries to run this algorithm near criticality, then like the sort of like the times that you have to run the Markov chain to say obtain independent samples from this Boltzmann distribution runs increases with with some power of the system size, and that's what's usually called as the critical slowing down, no? Which means that the performance of these local algorithms near criticality takes a severe hit. Or like another instance in which they also suffer quite a lot is in the presence of frustration, no? Because then like the energy landscape like becomes really ragged, and then just proposing spin flips is not like the most efficient way to move like from one place to another, no? And then this translates in actually like having to run your Markov chain for a time that might be like exponentially large on the inverse temperature or something like that, and that really sets a limitation on the kind of the system sizes that you can study and the temperatures that you can study with these kind of algorithms, no? And I mean, like once it was realized this kind of problem, so like there were like other proposals to say carefully like construct like more efficient proposal probabilities, no? And for instance, like these are cluster algorithms that I haven't not included here, which I'm sure that some of you are as well familiar with, like such as the Wolf algorithms or algorithms like that. But these algorithms like really rely on, say, some insight from the underlying physics, and generically that they are not hard to construct, no? And something else that one could think about doing is to take some proposal probability, which is just some probability that one can sample from, that only depends on the final configuration, no? So say I have some probability p tilde, some probability distribution p tilde on this same configuration space that I'm able to sample from, and I'm also able to compute the weights of this probability, the probabilities of this probability distribution. Then by sampling it, And I can use it to propose moves for my Markov chain, and I can correct them with this Metropolis Hastings filter. And say so in general, like the performance of the algorithm will depend on how good this approximate probability distribution mimics the correct probability distribution P without the tilde. And yeah. And just that, well, actually, like the point of our work will be to construct this this probability distribution that approximates the true Boltzmann distribution with tensor networks. And because with tensor networks we can approximate it quite well, we will actually be able to construct an algorithm which is very efficient on, say, like moving across the configuration space. At the same time, we will also benefit because something that is like really good about like these Monte Carlo algorithms is that the only error that they have is statistical, as I said before. No? And tensor networks do not have like this property because say if you get some result from some tensor network simulation, then you don't have like a way to know what is sort of like the distance to the true value. You know? And then by correcting this bias of the probability distribution that we obtain with tensor networks, then we will be able to have like results that have like only statistical error. Okay, yeah, so now I will try to say switch gears to sort of like describe how to construct with tensor networks an approximate probability distribution P tilde that sort of like tries to mimic or like tries to be as close as possible to the Boltzmann distribution, and that and I will try to highlight also like how to sample from it and how to evaluate the weights, and then I will try to show the results of using this probability distribution to actually propose moves for a Markov chain. So to motivate this part, or like to see how this construction, it is useful again to go back to this classical Ising model on a square lattice. No? And as we saw before, then we had like some Hamiltonian that was like a function of the different variables. No? And then we also know that the partition function of this model can be written as just like the sum of over all configurations of these Boltzmann weights. No? And then by doing a similar trick to the one that is used to solve, say, like the one-dimensional Ising model, I can write this as a product of matrices. No? So when I try to solve the Ising model in 1D, or like any classical spin model in 1D, what I have to do is to introduce like these transfer matrices. No? And then I introduce one transfer matrix, which is like some factors of the exponential of minus b, that has, I introduce like one transfer matrix per bond. And then like say the indices of the matrix correspond to the physical spins. No? And this contraction is actually not exclusive to 1D, and one can also do it in 2D. The only difference is that one has to be a bit more careful with the kind of, say, contractions that he does on each vertex. No? So yeah, like recalling what we do in 1D, no, we have like this sum of some products that we want to approximate with, and we write this Boltzmann weight, like this contribution from a single bond to the Boltzmann weight, as a matrix, no, that has these matrix elements. And this matrix where the two indices of the matrix correspond to the spin variables on, say, like the bonds that are nearby say, well, yeah, like on the vertices that are nearby this bond. And this is drawn in tensor network notation as, well, like this matrix with these two indices is drawn in tensor network notation as, yeah, like this ball which represents the matrix, and these two legs which represent the different indices. And then if we were studying in 1D, the partition function of this model in 1D would be just like the product of all these matrices, no, standard. But because we are studying problems in 2D or even higher dimensions, then the contraction of this matrix has to be a bit more careful, and it has to take into account that whenever there's like two bonds that share the same, say, vertex, then in the contraction, this vertex has to take the same value. No? Yeah. And in this manner, like one can write like the partition function. Actually, yeah, like I've done it here in 2D, but the construction is general, and one can do it in 1D, 2D, 3D, or like even like in different lattices, as what people call like usually a tensor network, which is just a bunch of matrices or tensors, higher dimensional tensors that are contracted in a specific way, you know? So are multiplied with some order across the bonds. And what it is also useful is that in this tensor network construction, it's not only possible to write the partition function, but it is also possible to include, say, local observables or two-body observables by just appropriately changing the individual pieces of the tensor network. No? And yeah, so just by rearranging the pieces and by doing some matrix decompositions, I can actually convert these like cumbersome structure where I have like one matrix per bond, and then I have like these contractions that take place on the individual vertices as something where my tensors live on the vertices. No? And now I have like these blue tensors that represent, again, like this. The blue tensor has 2 legs, so it's a matrix, and this one has 3 legs, so it's like a 3-leg tensor, tensor with 3 indices. And this is like whenever there's like 2 legs of this tensor that are joined, they just mean that these legs of these indices of the tensors are contracted one with the other. And yeah, like this is what usually people call a tensor network, and it's there's like really efficient algorithms actually to try to contract this tensor network. So, and by contracting, I mean like just being able to compute the value of this matrix, well, this tensor multiplication. And in general, like these algorithms work for say like any tensor that I may put in here. So like it's not exclusive like to models that come from statistical mechanics, and I can also include observables. So it's not, like I can sort of like modify, no? And regardless of the, say, like components of the tensor that I write in here, these methods are going to, say, give me a value for the contraction. But something that I should mention as well is that like these methods for the, say, computing this exploitation value, in general, I can only give an approximation to these 2 exploitation values. So they can only be approximate. I mean, I cannot have a guarantee on how well they are going to perform. Okay, so I hope I convinced you that by multiplying these matrices together, or like by appropriately multiplying all these tensors, I can obtain an estimate of the partition function. And at the same time, I also can obtain estimates of some observables. Say. And for instance, like one observable that I can compute is an observable that is a function of like the entire configuration. That is one only if the first spin of the system is, well, like any first spin, first spin of the system has a positive value, and is 0 if that spin has a negative value. And if one actually like computes, like the expectation, well, theoretically, the expectation value of this observable actually like just matches the probability. I mean, like if I were to do it exactly like this, would match the probability of the first spin being up. And because this is just like a local observable, it's something that I can try to compute with my tensor network, and then I can try to approximate it with it. No? So I can try to compute the partition function and this observable with where I've restricted the configurations that only have like a plus on the first spin, and then I can approximate the marginal probability of the first spin. And once I've done that, I can sample according to it, and I can fix the value of that spin. No? And then I can move to the second spin, and I can play again the same game. No? So now I have, say, the value of one spin fixed, and I can compute an approximation to this observable that gives me the marginal probability of the second spin condition on the first spin being on the value that I've already sampled. And then I can sample from it again, no? Which is this formula that I've written again, where I just use Bayes' theorem. No? And in this manner, like I can iterate across my lattice, sampling a probability distribution that is not exactly the Boltzmann distribution, but approximates the Boltzmann distribution. And in this manner, I can, at the same time, like I can sample from this probability distribution P tilde that is constructed from tensor networks, and I can also evaluate the weight of that probability distribution. So this P tilde. And if I'm careful, like with the intermediate computations that I'm doing, the effort that I have to that I have to make to actually compute this, to obtain these samples and to obtain these values only scales linearly with the system size, which is what we expect. And that's great, because then we have like some probability distribution that approximates the desired probability distribution, but we don't have a certainty of like how close it is to the probability distribution, but we can use it to, say, propose moves for a Markov chain. And through the Markov chain, we can correct the bias of this probability distribution and obtain samples from the underlying Boltzmann distribution. And because this proposal probability is independent of the current configuration that we have, if we are able to propose many moves with this new scheme, if our proposal probability gives us new configurations, then there's going to be like less correlations that in a standard metropolis algorithm where we were just flipping a single spleen. And in this way, we will be able to say like move across the configuration space much faster than usual local algorithms. Okay, so this was sort of like the technical explanation, I would say, of the scheme of the Monte Carlo ingredients and this how to approximate this Boltzmann probability distribution with tensor networks. And then I will move on to just commenting the results that we get when we use this probability distribution that comes from tensor networks to propose moves for a Markov chain. And the first question that one may ask is, take a simple model, say the Ising model on 2 dimensions on a square lattice with homogeneous couplings that I try to draw here, and try to see how often do we get updates with this Markov chain that we propose. And actually, there's something that I forgot to mention, that is that when using tensor network techniques to say compute these expectation values, there's one parameter that one has, which is usually called this bond dimension that I write it here as capital D, bond dimension, that controls both the accuracy and the numerical effort that one makes in this computation. So the higher the D, the higher the cost of the algorithm, and at the same time, the higher the accuracy that one expects to get from for the results. Okay, but getting back to this, I was commenting that the first thing that we looked at is how often do we get updates, And then I can take this simple model, the Ising model with homogeneous couplings, and then as a function of the temperature T, I can look at how often do I get rejections if I propose moves with this approximated probability distribution for the Markov chain. And then one can see that the number of rejections that I have on this Markov chain increases near criticality. And actually by increasing a bit, not by making a huge increase on this bond dimension, on this parameter that captures the numerical effort that I'm putting on my tensor network algorithm. By doing a small increase in it, I can actually make the practically rejectless. So say if I propose 100 moves, then I will have 99 acceptances and maybe 1 rejection. But this is a quite simple model, and something else that we can look at it is is models that have, say, some frustration. And the next model that we looked at is what people refer to as the fully frustrated Ising model. And this model is still a model of the Ising model. So it's binary variable sitting on every vertex of the lattice. But now the bonds across a plaquette have values in such a way that you cannot satisfy, say, the energy across all possible bonds in a plaquette. So the idea is that the coupling in this direction would be, say, +1, +1, +1, and in this one, -1, in such a way that, at the same time, you cannot satisfy, say, you cannot minimize the energy on all bonds, and then you have to concede on one of the bonds, and that creates sort of a complicated energy landscape. And then one can look at the same thing, as a function of the temperature, how much do I need to increase the computational effort to have a given a small number of rejections, and this is exactly what is plotted here. And this model, as similarly, a bit different. But in this case, it has a zero temperature phase transition around here, where we expect our method to not work really well. And this is sort of for a given size. I think it was for systems that were 32 times 32. But then we can also look at, say, if we scale the system size near criticality, how do I have to scale this parameter that controls the accuracy of the method? And this is exactly the next plot that I have here. So here I have again these say rejection rates of my Markov chain as a function of the system size for a homogeneous Ising model, so with all the same couplings, and for different for increasing system sizes. And one can see actually again that for small that even with modest effort, then one is able to sample quite accurately from this probability distribution, and one is able to propose to construct Markov chains that say accept a move like 80% of the times. No? And one can do like this plot. I think it was exactly at the critical temperature of the Ising model, and one can do the same for this fully frustrated Ising model near the zero temperature phase transition, and then one can see that the increase and the performance is a bit worse because there's frustration in this algorithm, but still, like even with a modest numerical effort, one is able to achieve like high acceptance rates for like systems that are quite large, like 128 times 128. Okay, but this is just an heuristic measure of how often does our Markov chain propose updates. So, but it's not a true measure of, say, the correlation that we have between successive samples or how fast our Markov chain converges to the equilibrium distribution, which is in the end that what we're interested, because like these time scale really are what limits the number of samples that we can obtain and really control the effort that one, like the time that one has to run the Markov chain to, say, obtain samples from it. And yeah, be able to compute expectation values from them. And in order to test these sort of like these equilibration times, so like the times that it takes for the probability distribution to converge, well, from the, so like the times that it takes from the initial probability distribution to converge to the Boltzmann distribution, a particularly useful test is to study an Ising model with Gaussian disorder. No, well, here's like the explanation that what I was trying to say. Samples obtained from a Markov chain are not guaranteed to be from the equilibrium distribution or uncorrelated. And then one has to do tests to sort of like see when we get to the equilibrium distribution or see when we get like uncorrelated samples. No? And in general, like doing these tests rigorously is very hard, no? But one can do heuristics to estimate them and take them into account in their simulations. And particularly hard test that we did for our model was to take an Ising model that again lives on a square lattice that has Gaussian disorder, no? And then one needs, well, because this is a model with quench disorder, one needs to say compute for a given realization of the disorder, compute the statistical mechanics of it, so to do average over the Boltzmann distribution of that model, and then once you have the average on this, yeah. So like the energy average over like one realization of the disorder, one can compute disorders over the average. So averages over the disorder realization. And it is useful to look into these kind of models because they satisfy for the matter of looking at the equilibration of a Monte Carlo scheme, because they satisfy an non-trivial relation. And actually, by taking a look at this expression that I've written here for the disorder average energy, one can see that by integrating by parts with respect to the probability distribution of the disorder, one can obtain a non-trivial relation between the expectation, well, like the disorder average value of the energy and a particular two-point correlation function of the system. And there's like this quantity, delta, which if one is indeed sampling from the probability distribution, it should be 0, because there's like this non-trivial relation that we've been able to derive because of the presence of the disorder. But the nice thing about this quantity is that if we start our Markov chain in say initial configurations that are uniformly distributed, so you're like just sampling zeros and ones randomly without taking a look at them, then the expectation value, like the disorder, well, the value of this energy is 0, and also like the value of this two-point function is 0, no? And this gives us that this delta is something which is of order 1. And as the equilibrium, so as we run our Markov chain, if we compute this delta as the equilibrium distribution is approached, then this quantity goes to 0, no? So just running your Markov chain, computing this delta as a function of the time step of the Markov chain, and seeing when it approaches 0, it's a good time step for, well, it's a good benchmark for the checking the ergodicity of the scheme. And this is exactly what we do in this plot here. So here in blue, I have like this quantity delta plotted as a function of the number of time steps that Markov chain Monte Carlo scheme needs to converge. And here in blue, I have the results of our method. No? So just using these tensor networks to propose the moves in the Monte Carlo, in the Markov chain. And one can see actually that with a small number of time steps, so yeah, out of the order of 10, one can actually get to this, to sort of like this value. One can get this value to 0, which sort of indicates that the system has equilibrated. And at the same time, we add for comparison like the results of this article, which is an article about like spin glass, developing an algorithm for spin glasses in 2015, where they come up with a clever way to do something in these kind of models. And like doing like some kind of cluster algorithm for like these models. And one can see that, well, actually like here are the results of like just using parallel tempering for doing the sampling. And here are the results of just combining like this parallel tempering with some cluster moves that come up with the way that they come up with on this article. And then one can see that, like these are some, I would say like these are some state-of-the-art algorithms. And then one can see that by using by using these tensor networks to propose the moves, like one can actually reduce the number of the time steps that one has to simulate, like by a factor of more than 100, I would say, because we're using like these tensor network to propose the samples. And okay, so another quantity that is also useful to measure like to benchmark say how well a method, a Monte Carlo method works, is to look at the autocorrelation, no? Because I mean, even when we've gotten to the equilibrium probability distribution, then people like still run this chain and like they get samples from it. No? But if you take samples that are not really separated in time, then you still have like some correlation between these successive samples, and then this increases the variance of any observable that you may compute using this correlated sample. No, so even if you are in the probabilities like in the equilibrium, you've sort of like reached the equilibrium distribution, you still need to wait, say, sometimes some decorrelation times between like extracting samples in order to have like sort of independent samples. So, and the way that people try to compute these time scales to determine these correlation times is by computing these 2-point functions actually in time of the Markov chain. And again, by like the theory of Markov chain, these 2-point functions should decay exponentially with some time scale tau that controls the decay. And this is actually a computation done for I think for like this Ising model here that has some frustration. One can see that by using these like this tensor network algorithm to propose moves for a Markov chain, one can greatly reduce the number of time steps that one needs to simulate to obtain independent samples. No? And again, the higher the computational cost that you put in these tensor network contractions, the better that this method performs, and the less correlated that the samples are between the less correlated that successive samples are.
Sorry, can I ask a question?
Yeah.
So how expensive to run this tensor network algorithm when you compare it with the Metropolis algorithm? Because now here we can see that there is a definite decrease, but like for example, for d equal to 8, if you compare how many hours does it take to run this d equal to 8, and if you compare it with the Metropolis algorithm, do we lose time from there? Or?
I mean, definitely, like they are a bit more expensive. No, so like the usual spin flip algorithm, like you just have to like pick a spin, change it, and then compute the energy. And that you can do super easily. And in these tensor network contractions, like they are a bit more sophisticated, but they are like a bunch of matrix multiplications, and they take a bit more time. But I would say maybe that they are a factor of maybe 100 slower.
100 times slower. Okay.
But it's not
is it probably with the system size? It depends on the.
Yeah, exactly. Like I would say like for this system size, but I mean like the I mean obviously like the effort grows with the system size, but
does it grow with the linearly or?
Exactly.
Not exponentially. Okay.
Yeah, like I tried to say before, but maybe because. So yeah, like I tried to say before here that if one is careful, like say the tensor network algorithm, then one can sample from it in an effort that grows linearly with the system size.
Sure. Okay. Thank you.
And that's exactly the same case for like spin flip algorithms, because then you have to have like at least a global change, you have to do like as many changes as spins you have, no, and then you have like the same increase. But yeah, I mean, like, I think that if you've never programmed a tensor networks, these may seem like something which is super costly and so many things, yeah, like very far-fetched, but in practice they are not that slow, no. And the problem is that like there's many of these algorithms that like there's many of these instances of the Ising model or like of statistical models that we need sophisticated algorithms, no. So I mean, it's not only like proposing spin freeze para change, but I don't know, like running 10 chains in parallel, like at slightly different temperatures, and proposing moves between these chains, which is this parallel tempering, no. And then, I mean, things get costly, I would say, quite fast with this kind of algorithms. Okay, but yeah, like I was saying here that yeah, like the correlation times are also decreased by using this sampling, and by a factor which is, I would say, quite large. And then, I mean, like something that we can do, I mean, like we know that it's probably because we're doing sampling, and in the end, like we're sampling the correct probability distribution, we know that we're going to compute the correct observables. No, but it's still a nice benchmark to do, is to look, for instance, yeah, like try to observe criticality with these samples, no? And here to do that exactly, like we've taken again a simple model, like the two-dimensional Ising model on a square lattice, and then we take as an observable the magnetization, no? And then we know that we construct this function g, which is called the Binder cumulant, which is a scaling function that is constructed in such a way that at the critical point, say, yeah, like whenever, so if you compute this at different temperatures and for different system sizes, at the critical point, this does not depend exactly on anything. So all the values should coincide at the critical point. And then one can do these sort of nice plots where you compute DC for different temperatures. And then, yeah, like at the critical point, they should all collapse at one point. And here, like with this, we can say that we can see that the critical temperature of the two-dimensional Ising model is 2.27, which is in good accordance with the exact result here drawn in these gray lines. And similarly, like, I mean, these tensor network techniques work better in 2 dimensions, but one can also extend them to 3 dimensions. It's a bit more costly, and the algorithms are not that developed so far, but one can also compute contractions of these 3-dimensional, so like these cubic tensor networks in this case, and one can also do, again, the same procedure. Like one can compute the marginal probability distribution of the first spin, then move to the second spin and sample from it, and so on. And in this way, and with the same effort that grows as linearly with the system size, one can also obtain samples from some probability distribution that approximates this probability, this Boltzmann distribution. And yeah, like here we showed our results on 3D. And actually, like what we try to show in this plot is that by using this sampling procedure, we can remove the bias of the underlying tensor network contractions. No? So here in green, in orange, and well, like it's green and red, what I've shown is the result of like just computing, say, say like the single contraction with sorry. So what I've drawn here for the 3-dimensional Ising model is the error and the energy if you just compute the energy from like the contraction from, well, the result that directly the tensor network give you. So here one can see that around criticality, tensor networks are not that accurate, no? Because like even increasing the computational power that one is using in this contraction, I still get an error, like something with a result which is of, but maybe a factor of 10%. But if I use these samples that I obtain from the probability distribution to, yeah, like use them to propose moves in a Markov chain, then I can obtain a result which is unbiased, no? Up to a statistical error which is unbiased. And yeah, and lastly, I would also like to mention that even though like it may seem that, yeah, like what I've discussed here like only applies to models that are discrete, yeah, like say the Ising model or the Potts model or something like that, one can actually do similar constructions for models that are continuous, no? So here, for instance, like I've drawn, or I tried to draw like the XY model on a square lattice that, as you probably all know, like it has this interaction term, well, it has like this angle that lives on every vertex of the lattice, and it interacts with the nearest neighbors by this interaction term with the cosinus, no? And then actually, like by doing a transformation, which is well explained on this article, I would say, but it is just actually like doing the series expansion of the Boltzmann factor across a bond, one can transform this model in something discrete, or like in something that contains discrete variables. And then one can also adapt our method and actually like obtain samples for this continuing model by using tensor networks. No? And here, because I mean like these are only preliminary results, I've shown like two samples that are sort of like successive in our Markov chain. No? And this is for this XY model, like living on a square lattice, and this is below the critical temperature because, well, this model has a phase transition, yeah, like some temperature. And these are successive samples from the Markov chain, and there one can actually see that although like this, I mean, like one can appreciate correlations in these samples, not because like most of the spins are aligned. There's like there's really no correlations between like successive samples. Like it's impossible to appreciate any pattern, and that's just because like the moves that are proposed are just non-local, like have new configurations. Okay, so with this, I would like to conclude, and yeah, like I introduced in this talk a new class of macro chain algorithms that work like for many body classical systems and that are based on tensor network randomization. And like I would say that the main breakthrough of our, or like the main idea of our work is to propose moves that are independent of the current configurations. No? And this is both, like from the theoretical point, this is a bit different to what people do in practice, and from the practical point, it's also quite different because it gives results that are quite good. And I would also like to emphasize that this is universal, no? Because like there's algorithms for say some spin models that work really well, but they are like really tailored to a particular model, no? And this one, in this sense, is like it's a bit more general. No? Like we don't care about, say, the specific couplings of some algorithm, whether they are positive or negative, but still you have this way of proposing moves for the Markov chain. So yeah, with this I'd like to conclude, and I thank you for your attention.
Right. Thank you very much for this great talk.